series. So let us draw the circuit again. Resistance, inductor, and capacitor all in series across an alternating EMF, source of alternating EMF. The current I will be common in both in magnitude as well as in phase. This is R, this is L, and this is C. And the drop across the resistor is called VR, potential drop VR. Across the inductor, VL, and across the capacitor, VC. And we know the phase relation between current and voltage in case of the component that is resistor. So I is the current, then VR will be in phase with I. In this case, in case of inductor, if I is the current, we know that voltage leads the current by 90 degrees. And in this case, I is the current and he is lagging by 90 degrees. And VR, that is the maximum potential difference, is given by I naught into R, VL, I naught L, and VC, I naught XL. XC. So we can show this with the help of phasor diagram. Suppose this is the OX, XX along X axis, Y dash. Now let us suppose the current I naught, the current is by I naught, that is along direction X direction along OX. Now the potential difference across R, the phasor representing this VR. We know these are two are in same phase. Let us suppose OA vector represents VR vector. Okay, or rather, the magnitude of OA is VR. So OA is represented by VR vector. Now VL vector, let us say it is because the voltage is leading by 90 degrees. So by 90 degrees we have the OY direction. And let us say this OB vector now. This point is B. So OB vector represents VL. The magnitude of OB is VL. And now in case of the potential difference VC represented by OC vector. Now the resultant of VL and VC, because VL, let us assume, is in magnitude, VL is more than VC, then the resultant will be along the direction, along positive Y direction. So let us cut this much portion from here, and we see that. So this is this much how we have taken VC. So this portion, let us say VB dash, is equal to VL minus VC. So resultant is OB vector, which is VL minus VC, and OA vector. The resultant of the two we can get using parallelogram law. So drawing the diagonal from point O to OK now represents the resultant of VR, VL and VC. Okay. So this is represented by the net. We can call this E naught. So phasor E naught is represented by OK vector, which is the resultant of VL, VC, and VR. And this phasor is making an angle, say phi, with the x direction, that is with the current direction in which the current is aligned, I naught vector. Okay. Now we can get the magnitude of E naught as well as the direction of E naught. So magnitude of E naught is given by OK, magnitude OK is equal to OA square plus OB dash square under root. Okay. You can either say OA square plus AK square. AK is now same as OB dash. So let us put the value of OA is VR square plus BL minus BC whole square under root. And OK is the magnitude of E naught. Now put the value of VR, which is I naught R whole square plus I naught XL minus I naught XC whole square under root. Now, I naught square get outside, R square plus I naught and square, so it will be equal to XL minus XC whole square under root. So I naught outside, R square plus XL minus XC whole square is equal to E naught. Okay, so this is the magnitude of the resultant voltage. Now the impedance represented by Z. So Z represents the impedance, is the effective resistance of this RLC circuit. The effective resistance of this RLC circuit is called impedance, represented by Z. So Z is equal to E naught divided by I naught is equal to R square plus XL minus XC whole square. Okay. So this is now let us find out the angle phi. So phi we can get from this triangle. So tan phi will be equal to AK divided by OA. Okay, what is AK now? AK is same as OB dash divided by OA. Now OB dash is VL minus VC and this is VR. So I not common, XL minus XC divided by I naught into R. So these two cancel. So tan phi will become equal to, I'll write down on top. So tan phi will become equal to XL minus XC divided by R. So we get the angle phi from here. So we have got both the magnitude as well as the direction. So therefore the resultant EMF at any time is given by E equal to E naught, that is the peak value, sine omega t plus phi is the phase. So this is the resultant EMF after three components, which are resistance, inductor, and capacitor, are connected in series. Okay, so we discussed three cases. XL more equal to XC, tan phi will be 0, tan phi will be 0, and that means it is a non-inductive or purely resistive circuit because I and E are in same phase. Now when XL is more than XC, it is inductance dominated circuit. So XVL minus VC is 90 degree ahead of I naught. So in that case, tan phi, because this quantity is positive, tan phi will be positive and hence phi will be positive. And XL is more than XC is more than XL, capacitance dominated circuit, the value of tan phi will be negative and therefore the value of phi will be negative. So impedance triangle, resistance R is given by rho L upon A. Impedance we know is the effective resistance offered by the RLC circuit to the alternating EMF. And reactance X is represents reactance, it is a resistance which is due to the opposing EMF. So opposing EMF which comes into picture when there is a change in the strength of the current. The change in the strength of current. So reactance due to the inductor is given by omega L, and due to XC, capacitance given by omega C, 1 upon omega C. So these are the resistances offered by the inductor and the capacitor. Now voltage across the capacitor leads. We know that voltage across the inductor leads and voltage across the capacitor lags. Okay, so net resistance we can find out the total reactance, because the total reactance is given by from this phasor also we can get total reactance is given by XL minus XC, and we can place plus minus in front because any of these two values be more than the other. So XL can be more than XC or XC can be more than XL. Depending on that, the value of XL minus XC will be either positive or negative. So from the three phasors VR, VL and VC, and VC, all these three phases we can get the impedance triangle. So what will be how we can draw the impedance triangle? In this triangle, we have a base, say OA, which represents the ohmic resistance, that is R, and a perpendicular drawn on it, that is XL minus XC, that is the difference between the reactance represented by say AB. And now let us complete the triangle OAB. So this gives us this is called the impedance triangle, and we can get the resultant impedance from this triangle Z, which is given by this. Z is equal to R square plus XL minus XC whole square under root. So this OB we can find out the resultant will be OA square plus AB square under root. So this is how we get the resistance, and phi gives the phase angle. So tan phi again is equal to XL minus XC upon R. So this is how we can get the phase also. So this is about the impedance triangle, which we get from the same phasor diagram that we have discussed in case of RLC circuit. Now reciprocal of impedance is called admittance. So Z we got R square plus XL minus XC whole square under root, and tan phi we got XL minus XC upon R. And now reciprocal of impedance is called admittance.